Good evening, everyone. So, welcome to this live session on week 4 of PS control systems. So, this is first live session for week 4, uh, and today is Wednesday, 22nd October, and Friday will today I'll give the overview of the slides, the content, and Friday we'll have the proper tutorial session. Okay, so let me show the slides. Yeah, so this is week 4 content. So basically, the outline what we are going to see in this is mostly on the time domain analysis for first order as well as the second order system. So the main motivation for doing time domain analysis is, so the basic question we need to ask is how to know the performance of the control system for a particular input signal, and how to design the control system uh, which meets a particular desired response and control requirements. So mostly this time domain analysis deals with what are different kinds of design specifications you need or you demand from the for your system to meet. Okay, so so basically, the time domain analysis it refers to the analysis of the system performance in time. Okay, so that means how do the different variables in the system they evaluate with the time. So there are mostly two common ways we have. So first one is natural response, natural time domain response, and forced time domain response. Another one is transient time domain response and steady state time domain response. We'll see exactly what are these two, and then we'll get into the first order as well as the second order systems. Suppose here, if you consider this RL circuit, if you consider resistor and inductor, they are connected in series, and here there is no source in the circuit. Okay, so and assume that inductor is already charged with some initial current. Let's say that current is of I naught. It means that in this circuit the current flowing in this direction is I naught. Initial current is 5 amperes. Okay, now if you write down the equation here for this circuit, so you'll have your equation this way. If you write down your KVL equation. Okay, now this equation if you solve, okay, we will be getting IL term as IL of t as IL of 0 e power minus r by L t, where initial condition this IL of 0 is 5 amperes. It means that your system will start at 5, and here we have this e power minus r by L t, right? So as t gets keep on increasing, this term, okay, this term gets reduces because it is e power minus some constant into t. So that's why at whenever time is very high, so this total current is getting to 0. Now in this, if you see, this is called as the natural response. Why? Because there is no source in the circuit. Okay, now, so hope you understand. If there is a source, we call it is as a forced response. So that is the difference between natural and forced response. Then if you see this curve, the current curve, where from time 0 to almost at 1.2, okay, so the system response is getting decreasing. Okay, after at 1.2 it almost became 0. From 1.2 onwards it is maintaining the 0 value. So we call between 0 to 1.2 this particular response as transient response, and from 1.2 to 2 the response is 0 or some constant value, we say that is as steady state response. Okay, So now you know the difference between the natural response, forced response, transient response, and steady state response. Okay, in both natural as well as the forced responses, we'll be having both transient and steady state in each. Okay, now so forced response. Now for the previous circuit, we are adding this source. We call that is as whatever the response or current flowing in this network, we call it is as the forced response. Again, if you write down the equation here, you'll have the equation like this. So this is the KVL equation of the above circuit. Okay. Again, if you solve that equation, so you'll be getting this I of t. Solution of this equation is I of t. Right. Again, if you see in this, when t becomes 0, e power this expression will become 1. So 1 minus 1 is 0. So it means that your response starts at 0. As t gets increasing, okay, this term becomes 0. Hence, final term is going to be V naught by R. So that means this one. So what is V naught here? 20. What is R? 10. What is V naught by R is 2. Okay, the final response is going to be 2. So that is the forced response. Okay, you see the natural response, it is getting reducing, whereas the forced response, it is getting increasing. And again at 1.2, at 1.2, if you see, okay, the response is almost increasing. From 1.2 onwards, the response is constant. Okay, here also in the same way like the previous one, we call between 0 to 1.2. So the this waveform as transient response, whereas from 1.2 to 2 we call that is as steady state. Okay, it means that both in natural response we have transient as well as steady state. In the forced response also we have transient as well as the steady state. Okay, that is first point. Next, standard inputs. So generally speaking, input signals to any control system, okay, mostly they are not known what kind of behavior they have. So we might not know exactly. Suppose for example, if you see any disturbance signal coming as a input signal, okay, sometimes, so we don't know what kind of behavior the disturbance has, because disturbances are mostly very noisy signals. Okay, so but there are some standard signals or standard input signals, okay, which we know already. One is unit impulse, unit step, ramp, and parabolic and sinusoidal. These are in control system. These are generally called as the standard test inputs. Standard test inputs. So what we do in practice is, so we'll try to see the response for these standard inputs, and most of the times these unknown input signals are mix of one or more of these standard input signals. It means that if you know the response of any system for these standard input signals, so it is very apparent that we can find the response for the unknown input signals also, because unknown input signals are can be written in terms of these standard input signals. Okay, so the basic necessity here is to start our study to find the response of the signal systems to these standard input signal. That's what we are going to do. That is the first point. Second point is, if you see any complex systems can be divided into smaller subsystems. Okay, the smaller subsystems are maybe the first order or maybe the second order mostly. Okay, so we can have the higher orders also, but the basic orders are first and second order. So it is for first and second order, if we can do the clear cut analysis, the further systems could be easy, higher order systems. Okay, so that is the reason why we start our analysis with the first order systems. Okay, so let us consider this closed loop system. Okay, so here what is the uh, transfer function is output by input. So that is written as 1 by tau s plus 1. Okay, so hope you know how you are writing this. So let us call this is as z, this is as h. Okay, so this is as some error signal. Okay, so uh, our ultimate aim is
Hello.
to yeah,
Sir, for the parabolic signal,
yeah,
in
yeah.
in one of the graded assignment question, they asked
Mm.
to put r of t as a parabolic, where I
Okay,
put parabolic as a unit 1 by 1 as a t square. Then I got there s to in s domain I got the Laplace 2 by x cube, right?
okay, yeah, yeah, correct.
But after the solving it says it is not a unit parabolic.
I mean, what is the signal you took? T square.
Yeah, for the in the in one of the questions, I wait a second, I will
Okay,
tell you the
can you
question.
ask at the end?
Okay, okay.
Yeah, that would be better. Mm. Okay, thanks. So now you have this closed loop system. Okay, so consider this is as some G, H, and E. Okay, you can write down the equations. What kind of the equation, or how can you write the equations? What is Y? So Y is going to be E multiplied Z. Am I correct? Yes. Okay, then okay, so that is Y. Then what is E? E is going to be R minus, okay, then Y multiplied 1. Why? Because Y comes here, it gets multiplied with this 1, and here what we get, so here H is 1, okay, what we get Y, okay, so E is nothing but R minus Y, so you can substitute there, you can substitute here R minus Y into multiplied Z. Okay. So what we get, we equal to R Z minus Y Z. Okay. What we can write here, 1 plus Z, correct? Multiplied RZ. What is Y by R is going to be Z by 1 plus Z. Am I correct? Z by 1 plus Z. Okay. Now if we substitute Z as 1 by tau s, you will get this expression. 1 by 1 plus tau s. Okay, this I think this is clear, there is no issue. Okay, here the tau, what we call it is as time constant of the circuit. Okay, basically that tau characterizes the speed of the response to a particular input. Okay, so if your time constant is very high, you'll have the slower response. Okay, so it reaches the steady state very slowly. Okay, the time constant is very less, you'll have the faster response, and vice versa. Okay, so it always defines the how fast or how slow your response is. So this we call it is as the transfer function of first order system. This one, first order system. Okay, so that is first point. Next, let us consider this example. Here we are taking tau as 0.5. You're taking tau as 0.5. Okay, now for this take this step input. That means your y of s as 1 by s. Okay, step input transfer function is 1 by s. So then u of t, u of s goes this side, you'll have this 1 by s here. Okay, so again divide that into partial fractions, you have this response. So time response. Okay, so y of t is nothing but what? L inverse of y of s. Take the inverse Laplace for this, you get this. Okay, now for this, if you substitute t is equal to 0, this term goes to 1. So the total term is 0. Okay, when t is becoming infinity, this term goes to 0 and the total term is 100. Okay, so that is how the response is getting increasing. Okay, when you apply the step input which is of amplitude 100, that is first case. Okay, hope this is clear. So here we took the tau as zero point 0.5. Here now you can see at what time it is reaching 100, almost at a 3. Now take tau as 2. Okay, follow the same thing. This is what you are getting. Okay, again if you check, okay, here this is e power minus 2t, whereas here we are getting e power minus 0.5t. Okay, so now if you see here, what is tau? Previously the tau is 0.5, so it reaching the response in 3 seconds itself, whereas now it is reaching response or 100 at 12 seconds, because when the tau is very high, okay, the response is slower. That is the main indication of the tau. It decides how speed or how slow your response is. That is for first order system. Okay, so now let us consider both the natural as well as the forced response. As I said, natural response is nothing but without source. Forced response is nothing but with the source. Okay, so previously we have seen without source, this is the response. Okay, so this blue curve represent this one. Okay, whereas the red curve represent this signal. Okay, so that is forced response. Okay, forced response, this is this. Now you see in both the cases, okay, here tau is called as the time constant of the circuit. So let us say if you take your tau as L by R and substitute in both these expressions, okay, this as well as the this, okay, what you are getting is, so take tau is equal to L by R, substitute in both the expressions. What you will get here is natural response is 0.368 I naught. That means this one, this response at a tau is equal to L by R. Okay. So for some values of L and R, whereas the other one forced response is 0.638. This one. So for the same tau value, okay, for the same tau value of L by R, so this is 0.368, this is 0.632. Now you can define the tau as the time taken for the response to reach 0.368 of the initial value, or the time taken for the response to reach 0.632 of the final value. Okay, I hope this is clear. That's what the definition says. Okay, the time constant tau is for a first order system is measure of how quickly the system respond to the changes. It is defined as time it takes for the response to reach approximately 63.2% of the final value for the when the step input is applied, or 36.8% of the initial value. This is for final, this is for initial value. Okay, that is how we will define the time constant. Okay, in general, okay, in general, let us say we are defining the transfer function as this way with the different time constants. For a first order system, we will consider only the first term. For second order system, we will consider the second term as well. Okay, so that is the time constant. So suppose you can see this in a general transfer function may be defined like this, where so this is nothing but numerator by denominator. Okay, numerator n of s, that polynomial we are dividing this way, denominator d of s we are dividing that polynomial as this way, where the pi's are called as the poles and zi's are called as the zeros. What are exactly these zeros and poles we'll be discussing in the further lectures, but let us see what exactly the importance of this pole is. Okay, so let's say when this pole is greater than 0, it means that root of this d of s is greater than 0. Okay, so the pole is located, s is less than 0. Okay, so then this exponential expression decays, because this is what we are going to get. Let's say for first order system, This is how the response, because you'll have only one pole because order is 1. Okay, for this if you take the inverse Laplace, you will get h of t as e power minus ptk. If p is greater than 0, this is e power minus some at. Okay, as time gets increases, the response decays. Okay, so and we say that the system is stable. Why? Because the response is going to be, as the time gets increases, the response is going to be something like this. After some time, it gets stabilized to 0 mostly. So that is first case. Second case is when p is less than 0, here you will have a plus quantity. This will become positive. So you'll have some kind of e power at. So when e power at, okay, so then here the exponential expression starts growing. That means you'll have the response. It starts at 0 and it goes like this. I'm sorry, not like this. It starts at some point, same point, let's say. It goes keep on increasing like this. It never gets settled to any value. Usually the value is k here. When you substitute t is equal to 0, it will become, irrespective of whether p is positive or negative, you will get k. So in both the cases, it starts at k. When p is negative, it decreases this way. When p is positive, it increases exponentially. Okay. So then we can say that the system is unstable. Where in first case, system is stable. Here in this case, system is unstable. So we can write here as tau as 1 by p, this one. So how can you write this one as k by, okay, 1 by ps plus 1, correct? That is p. This is how we can write. So this is your tau, okay, tau 1 k, 1 by tau s plus 1. That is the expression we should have. So hence, so tau is equal to 1 by p. That is the time constant and pole relation. Okay, time constant and pole, they both are inversely proportional. Hope this is clear. Okay, so then this is what the response transfer function we have. Okay, so now what is basically the transfer function says y of s by r of s, correct? Now take your r of s as impulse signal, unit impulse. That means r of s is going to be what? R of s is going to be 1. Okay, substitute here, then your y of s expression is this. Okay, when you substitute r of s as 1, so this is your expression. Okay, y of s expression. Then take the inverse Laplace. So this is your y of t. Okay, y of t. So 1 by tau e power minus t by tau. Okay, so now if you see here, so this is the transient term. Okay, so transient term. This term represents the transient term, whereas steady state term is always 0 for different values of tau. Okay, so tau is when it is 0.2, the response taking less time. Tau is 0.8, the response is taking more time. You can see that. Okay, so now again, if you see here, so again, if you see here for the blue curve, maybe from 1.2 onwards. So before that, the response is keep, it's not reduced to 0. So we call that is as transient response, and this is steady state response. Okay, transient state and steady state. So when we give this impulse signal, this term would becoming 1, which giving us the this as the response. Okay, now give the step signal. Okay, now this would become what? 1 by s. So here you'll have 1 by s. Okay, so now again, if you apply the inverse Laplace, you would be getting like this. Okay, here this part is the transient part, where that is y transient, whereas steady state part is going to be constant k. It means that simply what we do for the substitute, keep substituting the value of t. Okay, it starts at 0 and it gets settled to what? This k. Okay, so this is nothing but k for different values of tau. Okay, here tau is 0.2, here tau is 0.6. That is the step response. Now you see the difference. So impulse response, the value is becoming 0, final value. The step response, the value is getting settled to some constant k. Okay, next. Similarly, the ramp. Okay, so again, so ramp signal, you know, R of s is going to be 1 by s square. Okay, then you will get this as the inverse Laplace. Out of this, the second term is the transient term and the steady state term is the first one. Okay, again for different values of tau, you can see the response. Okay, when tau is 2, when tau is 3. When tau is 2, the response will be faster. When tau is 3, the response will be slower. Okay, so what we saw in this is quickly response of first order system for different inputs. Okay, and the definition of time constant. Okay, next. Okay, so now we'll see the same similar concept for the second order system. So now you can see previous circuit, what we have considered is the R and L only. Okay, whereas now we are considering the capacitor also. Okay, so now here R is a resistor is a general element, whereas inductor and capacitor, they are the energy storing elements. Energy storing elements. Okay, so here we have two elements. Okay, so L and C. Hence, so our order of the system is going to be 2. So that means order of the system will be equivalent to number of energy storing elements. Okay, so now for this, if you write down the KVL again in the same way, previous way, so this is what the equation we are going to get. Okay, since there is no source here, so this is the KVL for the uh, above loop. Okay, since there is no source here, so we have this 0 here. Okay, now taking the Laplace transform will give us this equation. Okay, so depends upon the roots of this equation. Okay, whether the roots are real roots, complex roots, or repeated roots. Okay, will have different behavior. Okay, for example, when the roots are complex roots, which we also call it is as the underdamped case. Okay, so we'll have the solution in this form. We'll have the solution in this form where alpha is r by 2l, omega naught is 1 by root lc, omega d is root over omega naught square minus alpha square. When the roots are complex, that means the values of l and c in such a way that if we find the roots of these using our regular quadratic equation roots, that is minus b plus r minus root square minus 4ac by 2a. If we use this equation and find them, if the roots are complex conjugate, okay, so that comes under as underdamped case. This is the equation solution format. Okay, now if you see that for these three values of RLC, okay, now you can see, so the response is damping in nature. and finally it is getting settled to 10. It is getting settled to 0. Again, if you see after 6 onwards, okay, up to 6, the behavior is something different. And after 6 onwards, the behavior is steady state. Now here you can see, so this we call it is as transient behavior. This is steady state behavior. Okay, so this is the natural response of the system. Okay, similarly, consider the forced response. It means that for the same circuit, you're adding a source of V of t, and if you apply the KVL, okay, so equation would be same. You are getting this new term V of t. Again, take the Laplace transform on both these sides. Okay, and again you will get the quadratic equation like ax square plus bx plus c. Okay, so now by finding the roots and by observing the case for these three values of RLC for the forced response. Okay, so the forced response, you could see the final value previously that was 0, whereas the final value that is 1. Okay, again, so you can see from 4 onwards. So this is the transient response and this is the steady state response. Okay, so this is how we will define for force and natural response. Okay, so we have two things, natural response and forced response. Natural response is also called as the zero input. Forced response is called as the zero state. Natural response means systems response to initial conditions with all external forces are zero, where the forced response is system response to external force. This is due to initial conditions. This is due to external force with zero initial conditions. Okay, so then again, transient response and steady state. As I said, the part of the response that goes to zero as the time tends to large. Okay, whereas the steady state response, okay, steady state response is the time response of the system after transients practically vanishes as time goes to infinity. Okay, the complete response is going to be summation of both the transient as well as the steady steady state response. Okay, so here again, as I said, most of these complex systems, so they are dividing into very smaller parts. So each smaller part could be a first order system or could be a second order system. Most of the engineering systems, okay, so like mechanical systems, electrical systems, biomedical systems, okay, so they are governed by these frequency components. Okay, mostly they are second order systems. They are of second order. We can represent or model those systems into second order differential equations. Okay, so that is the basic motivation for the second order systems. So this is the general form, like we have for first order system as 1 by tau s plus 1. So for second order systems, this is the general form. Okay, in this omega n is the natural frequency. Omega n is the natural frequency. Zeta is the damping ratio. Omega n is the natural frequency and zeta is the damping ratio. Okay, so now, so the system poles, as I said, they are nothing but this is the numerator and this is the denominator. Just a minute. Yeah, so we have the numerator as well as the denominator. If you consider the denominator and Uh, so if you consider the denominator, this is the expression we have, and find the roots. These are the two roots of the denominator. Minus zeta omega n plus or minus omega n root over zeta square minus 1. Okay. So based upon the zeta we have here, so if zeta is positive or greater than 1, okay, so this will be positive. If zeta square is less than 1, okay, this will be negative. Based upon that, we'll have roots, real, complex, conjugate, repeated roots also. So based upon that, we will be defining system behavior into three cases. Okay, so that is uh, underdamped behavior, overdamped behavior, and critically damped behavior. Okay, so let us say, so we got s as minus zeta omega n plus or minus omega n root over zeta square minus 1. So this we can write it is as just minus zeta omega n plus or minus j omega n root over 1 minus zeta square. I'm just reversing these two and adding this j term. Okay, what is this one basically? A plus jb, a plus jb. Okay, so that means it is a complex number. Where that complex number, what does it basically represents? It represents some number like this, where this would be like a, and whereas this would be as b. Okay, so considering these two, and you can find this alpha, theta, etc. Okay, so you can represent that pole. So this is the basic general second order system. Again, same similar way, you may consider this is g. Okay, apply the same way and find y by r. You should be able to get this expression, closed loop transfer function. Okay, so now complex roots, as I said, minus sigma plus or minus j omega d, where minus sigma is nothing but omega zeta omega n. Sigma is zeta omega n. This term only, first term. The second term is the whole term. Okay, so that is nothing but omega n root over 1 minus zeta square. Okay, so now you have minus sigma plus or minus j omega d. You can write that one as this. So minus sigma plus j omega d minus sigma minus j omega d. So if you multiply both the roots, so you'll have this s plus sigma whole square plus omega d square. Okay, where you have sigma as zeta omega n, omega d as omega n root over 1 minus zeta square. Where basically this uh, zeta, that is called as the damping ratio, which is a dimensionless quantity describing the decay of the oscillations. Okay, based upon the value of zeta, the oscillations uh, may decay fastly, slowly, or maybe different behavior. Okay, that is first one. Then next, so system's natural frequency, angular frequency at which the system tends to oscillate in the absence of damping force. Okay, then you have this system damped frequency omega d. So angular frequency at which the system tends to oscillate in the presence of the damping force of omega d is equal to omega n root over 1 minus zeta square. These are the three major definitions of zeta, omega n, and omega d. So mostly omega n is the natural frequency. So omega d is mostly the damping frequency. Okay, so now let us see the first case. So we are considering input as only impulse. Okay, so only impulse, this is the expression what we have. Okay, so this is nothing but minus sigma plus or minus j omega d. So this is the first case when zeta is between 0 to 1. So that we call it is when zeta is between 0 to 1. If you find the, take the zeta, that value, if you find the z of t, That means taking inverse Laplace transform of g of s. This g of t expression would looks like this. Okay, where this one has this sinusoidal term. Okay, so what does this indicates? Here we have two extreme cases. One extreme case is zeta is equal to 0. There is no damping at all. There is no damping, you see. So the response is pure sinusoidal. That means zeta is 0. When zeta is equal to 1, okay, you'll see the response of this one. That is called as the critical damping. Critical damping, this response. Okay, so here we have underdamped case. In between 0 to 1, you could see, in between 0 to 1, you could see the response starts here, oscillate, and then reduce. The response starts here, oscillate, and then reduce. Okay, I hope you can understand difference between sigma is equal to 0, sorry, zeta is equal to 0 to zeta is equal to 1. Okay, next. So impulse response. So mostly the zeta. Okay, so the actual response omega d slightly reduces as the damping ratio increases. Okay, so then next you can see at zeta is equal to 1, we call it is as the critically damped. Okay, so same response, take zeta is equal to 1. If you take zeta is equal to 1, the denominator here, this denominator, so reduces as s plus omega n whole square for zeta is equal to 1. We call that is as critically damped case. In that case, so if you take the inverse Laplace, we get omega n square t e power minus sigma t. Okay. So generally what we can see is, so here you have two terms. Okay. E power minus sigma t. It starts somewhere here. It reduces like this. So this is what e power minus sigma t. Then what we have is t. T would be like this. Okay. So I'm sorry, not like that. So T would be somewhere like this. Okay, so the overall response is what? Multiplication of these two responses. Okay, so it will be something like this. You can see this curve and this curve both are same. Okay, so that is what the response, which is also called as the critically damped. Okay, the other one is when zeta is greater than 1. So we call that is as overdamped case. All this is in the in light of the impulse response only. Again, consider the transfer function. Okay, take zeta is equal to 1 and divide that into two roots r1 and r2. Again, find this inverse Laplace. Okay, where r1, r2 are the roots or poles. Okay, again, if you see here, so you are keep on increasing the zeta. This is 1.2, 1.3, 1.5, 1.7, 1.9. You can see here. So as you keep on increasing the zeta value, okay, so this is how the response goes. So this is how the response goes over a damped case. So the damping, the oscillations gets reduced very fastly. Okay, so similarly, just replace the impulse with the step response. Again, the three cases. So first one is underdamped case. When you are having the underdamped case, so here what you are doing, so you are multiplying with 1 by s. You are multiplying with 1 by s. So divide this into partial fractions and apply the inverse Laplace. L inverse of y of s. Apply the inverse Laplace. So you have this expression, final expression. You have this final expression. Okay. So if you plot that expression, it looks like this, where you can see this So the oscillations uh, go to a maximum value here. This is what the value you wanted to get. So the oscillations will cross that value and try to stabilize to try to achieve this one after some time. It means that oscillations are as they go forward, they are trying to getting reducing. Okay, for different values of zeta. Similarly, when you don't have the damping at all, that means in this given here in this equation, first equation here, substitute zeta is equal to 0. So the second term becomes 0. When the second term becomes 0, you are left with this. So again, you are multiplying with 1 by s. Why? Because you are dealing with input. Okay, now divide that into partial fractions. Take the inverse Laplace. What we get? So for 1 by s, that is 1, and for this, that is cos omega n t. Okay, again, if you draw the response, that is 1 minus cos omega n t. This is what the response is. Okay, here that is purely undamped case. So it means that the oscillations will not reduce. Instead, they keep sustaining. They keep in the sustained mode. Okay, next. So critically damped when zeta is equal to 1. So substitute zeta is equal to 1 in this case. Okay, so you'll have a plus b whole square. The denominator can be written as a plus b whole square. So again, divide that into partial fractions. So find the inverse Laplace. You get this expression. Okay, in this expression, you'll see you'll have 1 exponential and t multiplied exponential term. Okay, so you could see this. It is slowly increasing and reaching the one value immediately. Okay, for this is called as critically damped case. Okay, next, over damped case. Okay, so the damping is very high. So taking zeta like greater than 0. So substitute zeta is greater than 1, any value. And again, you are taking the step input. So this expression, okay, this expression will give you the y of t. Okay, again, if you plot it, so the response is over damped. So it reaches to the 1 very fastly. You can see the response between this and this. Okay, so this seems to be reaching very fastly over damped case. Okay, so here we saw the second order system, 3 cases for different impulse as well as step input, under damped, over damped, and critically damped. Okay, next. So the major issue here is we are right now, as of now, we have seen the time response of the first order as well as the second order systems. So how this time response, okay, is going to help us in case of synthesis of the control system. That means in case of design of control systems. Okay, so what exactly we need to do? Okay, so here the motivation here is the we define something called as the performance specifications of the or time domains specifications of the control system. Okay, so the time domain specifications in also they have different specifications as rise time, fall time, overshoot, settling time. That's it. So these are different components. So using these components, we will use them to design a proper control system to our requirement. Okay, let us see one by one now. So generally, all these are defined for with respect to the response of a system. So response of a system, as we have seen previously, that is nothing but y of t. That is nothing but y of t expression or y of t plot. Okay. So let us see the first response. First definition as rise time. So the time it takes to reach vicinity of new set point. Okay. Settling time. So generally rise time what we call is the time taken for the response to go from 10% to 90%. That means 90% is very close to the new set point. Okay, settling time, the time takes the system transients to decay. It means that when it gets settled. Okay, then overshoot is defined as maximum amount of amount the system overshoots its final value. Okay, divided by the final value. Okay, peak time is defined as the time it takes for the system to reach maximum overshoot. Okay, now let us see one by one for the second order system. So the definition here you can see. Okay, first one is rise time. Rise time you could see. So this is the time from almost here to here. It means that this is the 0%, this is almost the 100% or 90%, 10% to 90%, close from 10% to here. That is called as this time is called as the rise time. Then settling time. Settling time is defined as what time it takes for the system transients to decay. So suppose if you see here, from here the system transients are getting reduced. Okay, within this band, they are trying to coming within this band. So then we can say this is the settling time. Next, overshoot. Overshoot means this is our reference value which we are trying to meet. So the waveform, how much it will go or how much it overshoots that value, this height. Okay, this is the reference we wanted to meet, but the waveform is going above that and coming back. So what is that overshoot? Is called as the overshoot, MP. And what is the time for the first overshoot? That is called as the peak time, this time. Okay, so we need to find the expressions for all these terms: settling time, peak time, rise time, maximum overshoot. Okay, so let's see one by one. First, rise time. So rise time is defined as time it takes for the response to go from 10% to 90%. Okay, by the way, this is of the this is for the y of t for the step input. Okay, we can have for ramp input, we can have for the impulse input, we can have for the other inputs also. But what we are doing here is the step input. Okay, what we do is this is y of tr, y of yeah. So what generally we do is, so we will find for y of 0.01 and we will find y of 0.09. I'm sorry. So we will find this expression at a 0.01, 0.1. We'll find the expression at a 0.9. Okay. Then we will substitute both. That means, so y of tr is nothing but y of 0.1 minus y of 0.9. This expression. So this is what we are getting the tr value is. Time taken for the response is this one. Okay, pi minus theta by omega t. Hope this is clear. That is called as the rise time. Okay, next. So this is the rise time. So you can see here rise time for different values of zeta. Okay. So for the underdamped systems, the larger the value of zeta, the rise time is more. The rest time is more because if the zeta is very high, the response it takes is longer. Okay. So rest time also will have more. Next, delay time. Delay time is the time required for the response to reach 50% of the final value at first instant. That means, so when you start here, okay, so this is your value, this is your reference. From this reference, somewhere 50%. Okay, so this is the time. So that time is nothing but TD. Again, expression is same thing. What you have to do is, so you have this expression, this particular expression. Okay, so in this y of t dd, so write the same expression which is equivalent to 0.5. I'm sorry, here previously here this is equivalent to 0.9 minus 0.1. Okay, now this is equivalent to 0.5. Okay, so if you substitute, you will get this expression as Td as 1.07 zeta by omega n. Okay, next, peak time. Okay, so peak time is the time. What we have defined is, this is your reference. So this is the waveform we have. So this time we call it is as the peak time. Okay, so that is nothing but the time at this point. The time at this point is what? So where the time derivative is 0 at this point. So that will be this one, because derivative is 0 here. Okay, again same expression. So you will find, you will be getting TP as this. So you will do these calculations, you will get TP as pi by omega d. That is called as the peak time. Hope this is clear. So peak time again. So this time. Okay, so similarly you could have the time for this, time for this, time for this, time for this. So we say this is as first peak, first underneath, second peak, second underneath, etc. Okay, then overshoot. So overshoot is this. Okay, so overshoot, we said that this is the reference, so this is the waveform, this is nothing but overshoot. From this final value, okay, final value means this one. Okay, how much overshoot it has, how much overshoot it has. So that is this expression. Okay, so if you find it, the final expression is this, because at that time the value is TP here, time value. Okay, this is the expression you have, that is called as the peak overshoot. Okay, so peak overshoots for different zeta values. For zeta is equal to 0.69, for zeta is equal to 0.59. Okay, so MP is 0.16 for this zeta, 0.05 for this zeta. Okay, 16% and 5% overshoot. Okay, so settling time, the time required for the response to stay within the tolerance band of 2%. It means that you have this waveform, the waveform goes like this. Okay, so tolerance band means this tolerance, so this is 2%. Okay, when that is 5%, so this is the expression. So you'll have this 4 by zeta omega n, 3 by zeta omega n. You can see here, so the settling time is inversely proportional to the damping ratio. Okay, so zeta increases, the settling time decreases. Okay, so these are the different time constants. So what are various things we have? Again repeat. So rise time, peak overshoot. So rise time, peak overshoot, settling time. Okay. Then delay time. Okay. So these are the values we have. Okay. So generally what we do is in designing the control systems. Okay. So we'll have some fixed values. We'll have some required values for the designer. What is my rise time? What is my peak overshoot? What is my peak time? What is my settling time? These are design requirements. Based upon these design requirements, we will design the control systems. Okay, for specific values. For specified values of these, the synthesis form of the above equations. Okay. So in general, the practical synthesis form means practical form. So we'll have MP, omega n. Okay, you'll have uh, different equations. Okay, so for example you would say like, so you have to find the allowable regions in the S plane for the both poles of the transfer function. Okay, so that is the question. What is the region on S plane which would satisfies this? Rise time would be less than or equal to zero point 0.6 seconds. The peak overshoot is 10%. The settling time is 3 seconds. Okay, so this kind of this is the design question. So you need to find this allowable region on the S plane. Okay, so that you wanted to satisfy this. Okay, so this is the design question. Clear? So are there any doubts or questions? Are there any doubts or questions? Let me go to the next one. Yeah, so let me quickly go through this one also. Yeah,
Sir, what if
yeah.
the tolerance is not 2 or 5? It is other than 2.
No, no, no. 2% or 5%, that is a requirement. Suppose, suppose for example, you are designing a control system for a rocket, okay, to follow an orbit satellite, okay. So you have your orbit is like this. You have your orbit is like this, okay. So this is what you wanted to follow. So then this is your reference, okay. This is the vehicle trajectory. So the question is, uh, what is this gap you want? What is the distance gap you want? Whether 2% tolerance or 5% tolerance or 7% tolerance, etc. What is that is your requirement? Is this clear?
Yes.
So that is designer's requirement. Okay, if designers want 7% is enough, you can have 7%. You can design your control system for 7%. If designer
Yeah, that's my
requirement
question.
is, yeah, yeah, if
Yeah,
designer
that's my
requirement
question.
is,
What if
mm,
it's 7% or a 10% other than this, then TS will be?
yeah, we have to do the calculations again.
Where can I find from
No, no,
where
not
I
needed.
where
I said, no, no, I said, let's say, let me show you. So this is your reference. Okay. This is what you are trying to do. Clear? So
yes.
this tolerance we are talking about, correct? The gap. Am I correct? Yes or
The
no?
error simply.
Yeah. So now you are saying apart from these, let's say I want for 7%, correct? So 7% means what? That is 0.07, correct? So your intention is, what is this time? That is nothing but settling time until you reach this point where this gap is 7%. Clear? Am I
Yes.
correct? Yeah, simple thing. So you have this 0.7%. It means that your y of ts should be equal to 0.07. Is this clear? sorry, not the
It will
0.07. It will be 1 minus 0.07. Is this clear? Or
yes
this will be
1
1
plus 0.
minus 0.07 by 2, because this gap, no, that is by 2. Is this clear? Yes or no? This
Yes,
is
sir.
0.07 by 2, this is 0.07 by 2. So you require only 1. So 1 minus 0.035. Am I correct? So that will be like point. So how much it will be? Zero point 0.9 or whatever the value is. So you'll have some x value here. Okay. Clear? What is this value? Let us write it. So 1.00. So 0.035. So what do I get? 5, 7, 9. Correct? 0.975. Am I correct?
965, right?
Yeah, 965. Okay. Yeah. So now equate that 0.965. You have this y
Sir,
of
9.96.
okay. Point 9 point,
9
0.965.
point
That is correct. No, no,
9.965.
no. This is 1.
Huh. That would be
Point 9
9.
only. 0.965. Okay, whatever it is.
Yeah,
So
point
you have
point
you
nine
have
six five
you
is
ha
the correct.
yeah, you have this expression now, y of t expression. Let me show you. Y of t expression you have. Second order system. Yeah. So you could see here y of t expression. Yeah, this one. Can you see this expression?
Yes,
Y of t. So what is this value now? 0.965. Correct? Yes or no?
yes, sir.
So substitute Ts here. Okay. So now
Okay.
given zeta, because system is known to you, omega n is known, omega d is known. Okay, in this expression. Okay, this value is what? 0.965. Okay, in this entire expression, okay, what is the unknown?
TS.
Yeah, that's it. You have to find Ts. Is this clear?
Yes, sir.
The
Means
Ts will
generally
be,
we,
uh,
yeah, yeah, please.
yeah, yeah. So the Ts is your tolerance for that 7%.
Means generally we go with 2% or a 5%.
Yeah, yeah, yeah. That is general case. Because that 2% or 5% that is theory only. But as I said, that depends upon the design requirement. Okay, so practically they may take something different. They some systems may want even lesser. Suppose if you see the surgical robots, okay, 5% and 2%. No, no, we cannot say. There should be even less, 1%, 0.5%, because surgical robots control systems should be very accurate. Got it? Okay.
Yeah,
When you
okay, sir.
design a control system for let's say stock market, okay, always you never want to have either zero loss or 100% profit. Correct? So let us say if your 100% profit is 1 lakh. So you cannot say that no, nobody would say that I want 100% or zero loss. Okay, if you get 50% profit is also fine. Yes or no? So it means that 2% and 5%, even people accept 10% also for some systems. Is this clear? So it
Yes,
depends, but the standard what we study in the course is 2%, 5% for general second order systems. Okay, I hope this is clear.
That means if I said if tolerance decreases, that means our
Ah,
settling time would increase,
obviously increases.
and vice
If,
versa.
if
Means if I want a
yes, yes,
lower tolerance, then my settling time will increase.
yes. Depends upon the system. If you want more tolerance, 0.00001 knots, you are expecting your settling time to be almost infinity.
So my settling time will
Ah,
very very
very
much
high.
high, very
Yes,
much
yes,
high.
yes. So that's why you keep the band. So keep the band for your acceptance. Okay.
Yes, sir.
Next, so yeah, so the final topic is steady state error. So basically, steady state error means again same thing. How much that band is there between, uh, I mean, how much that band you want for a system. Okay, for a particular system. Okay, how much steady state error, or what is the error between your actual output to the desired output as time t is tending to infinity. That is called as the steady state error. Okay, so basically actual output is nothing but what? Y of t. The reference input or desired input is what? R of t. Okay, so as time is tending to zero, tending to infinity, so that value gives you the steady state error. Okay, when the time is tending to almost to very far, almost infinity time, at that time, what is the error? Okay, so this we can find it easily. So if you see this expression, if you apply the Laplace transform, okay, so using the final value theorem, we saw in the in the time domain, the final value theorem says that in the Laplace domain, you can multiply with s and e of s. S is tending to 0. Okay. So what is this E of s is? I think starting of this lecture, this live session, I have derived this E of s expression in the same way. Okay. So you can substitute this one here. Once you know R and Z. Okay. So the E of s is what? Limit s is tending to 0. Yes, E of s. That can be written as s is tending to 0. Yes, E of s is r by 1 plus gs. This is very important formula. Okay. Now let us see for different systems. Okay, for the standard input signals for unit step ramp inputs. Okay, so for unit step we have r of s is 1 by s. Just a substitute here. Okay, so you're substituting r of s as 1 by s. So that 1 by s, this s and this s gets cancelled. Okay, so r of s also would be gone. So you have this. Okay, so that can be written as 1 by 1 plus kp, where kp is this, which is called as the position error constant. Okay, so that is steady state error for step input is 1 by 1 plus kp. Kp is this position error constant. For unit ramp, okay, so r of s is 1 by s square. Again, substitute here. You would be left with what? S here. Only one s gets cancelled. Okay, so then it can be written as when s is tending to 0, if you substitute, this s goes to 0 and only this part of the s would be left. So that is 1 by kv. That kv is nothing but limit s is tending to 0, s g of s, which is called as the velocity error constant. Here this is position error constant, this is velocity error constant. Similarly, you can extend this for the parabolic also. You will get 1 by Ka, which is nothing but s square Gs. Here you see the difference. This is G of s, this is s G of s, this is s square G of s, which is called as the acceleration error constant. Okay, I think we are running out of time. So I'll just take 5 minutes time. Is that fine?
Yes, sir.
Yeah. So 5 minutes, I'll clear these slides. this revisit would be completed. Then next week, next Friday, we'll have the tutorials. Just a minute. Yeah. So this is called as the acceleration error constant. Okay. So we have three constants.
Sir,
So
sir, I have
Kp,
a doubt here.
yeah, yeah.
I asked earlier as well.
What?
For the unit parabolic, it should be their Laplace will be 2 by s cube, right?
2 by? No, no, that constant we will not consider.
Why?
No, I mean, no, it is like what we take is for unit parabola, r of t, we take like 2 by t square. I'm sorry. It should be like t square by 2.
But it
It's
says
it's not actually it's not actually
unit.
unit. It's not actually unit. We must say that parabola with magnitude of 1 by 2. So if
The
you take
question
like
it is
this
not
only,
mentioned as well.
oh, okay, okay. If we take like this only, we will get r of s as 1 by s cube. Got it? 2, 1 by 2 and 2 gets cancelled. Okay, here in this case, this should not be the one. It's just parabola with 1 by 2 t square by 2. That means then only the Laplace will be 1 by s cube. Clear? Yeah, what is your question
Yes, sir.
now?
Yeah, this is my question itself. But
Okay,
if I
okay.
take the unit parabola, it will be 2 by s cube. Same thing happened in the week
Oh, okay,
4
okay.
grade did the
Maybe
same
question
thing.
is a question they should not keep the unit. Can you write mail again? We'll check that.
Yeah, I marked it the correct I because I see this the unit
Oh, okay,
parabolic
okay, okay.
is 1
Yeah,
by
yeah,
s
yeah,
cube.
yeah. This is the case. This is the case. When we say parabolic, we wanted to get our R of S as 1 by S cube. That's why we take R of T as T square by 2. That 2 gets cancelled. Okay.
Means for the parabolic we r of t we have to take t square by 2, right?
That should be mentioned properly. Yes. If I
Yeah,
say
please mention
parabolic,
in the
yeah, yeah.
question if
Got it.
it
Yeah,
comes
yeah.
in the.
Got it. Got it. Got it. Yeah. So now these are the three error constants we have. Kp, Kv, Ka. Okay. So using those, we can find this steady state error when that kind of inputs are existed. Okay. So when input is unit step, by knowing Kp, we can find steady state. When input is ramp, by knowing Kv, we can find steady state. When input is parabolic, by knowing Ka, we can find the steady state. Okay, so that's the thing. Then, so this is the visualization. So this is your reference. Okay, so this is your actual. Okay, this is your R of t. So you see the steady state error now almost 0.5. Okay, here steady state error is this one. That is at a time t, infinity. Okay, here the steady state error is this almost infinity. Okay, so the measure it measures what the steady state error. It measures the system accuracy. Okay, at a time tending to infinity, what is the gap between your actual output to the desired output? Actual output is what? Y of t. Desired output is what? R of t. Okay, so that measures as time is tending to infinity, what is the difference between these two? That is called as the measure of system accuracy. In ideal case, that should be 0. Okay, so R of t must match, sorry, Y of t must match the R of t. Okay, so what is our general requirement? It should be as low as possible. Okay, so basically it depends upon the two factors. One is the type of the reference input R of S, so what kind of input we have, and the type of the system also, because this KV, these three uh, KP, KV, KA, they are in terms of G of S. What is that G of S is very important. Okay, so that G of S type. So we'll see what exactly the type are. Okay, and also the steady state errors we will calculate only for closed loop system, not for open loop. Okay, so now let us see what is this type of the system is. So in general, we write our transfer function as this way. So we write to numerator and denominator. Okay, so numerator we write into roots. Okay, z1 z2 they are the roots, p1 p2 they are the roots here. But so this expression s power n, okay, this represents something like this, s power 0 power n, correct? That means this is the p value here, that is p is equal to 0. P is equal to 0 means what? Origin. So that represents n represents, so n represents the number of poles at the origin, number of poles at the origin. So now we can say that, so s power n represents the n poles at origin is called as the type n system, type n system. Okay, so as s is tending to 0, Sn dominates in determining the steady state error. Okay, now let us see one by one. So type 0. Type 0 means what? Here n is equal to 0. We can calculate. You know this expression, correct? Okay, so s is equal to 0 means what? 1. It does not make much difference. Okay, so here when s is equal to 0, this would become what? 0, and that will be infinity. Okay, when s is equal to 0, this is also 0, this will become infinity. So now what you see here, for type 0 system, okay, you will have a constant position error, kp only exists. Okay, infinite velocity, infinite acceleration at steady state. Clear? Any doubt? So only position error will dominate, not the velocity and not the acceleration. That is for type 0. Next, type 1. Okay, so type 1 means n is equal to 1. N is equal to 1. So then in that case, this will become 0. You will have only this. You will have only this, and this will become infinity. Okay, so here we will have only constant error. Okay, 0 position error, infinite acceleration error at steady state. Then type 2. Okay, type 2 means what? You will have 2 here. When you have 2 here, this will become 0. What is basically the expression is Kp, Kv, Ka. What is Kp is, we have seen. What is Kp is this one. Limit S is tending to 0, G of S. What is Kv? Limit S is tending to 0, S, G of S. Limit S is tending to 0, S square, G of S. So here G of S, that looks like what? 1 by S square N of S by D of S. Am I correct? Yes or no? So what is the Kp expression here? That's what I am trying to do. S is 0. So this will be what? 1 by S square. Okay, N of S by D of S. Yes or no?
Yes.
Okay, you'll get this one what? Infinity. So infinity. Okay. Similarly, here also, kv is what? Limit s is tending to 0. So that is yes, this yes. Then 1 by s square n of s by d of s. Okay, this s and this s gets cancelled. So that will become infinity. S is tending to 0. That will become 0. Similarly, here you'll have s square gets cancelled. You'll have ka. So you'll have constant acceleration error, 0 position, 0 velocity. These two are zeros. Okay, this is for type 2 system. Okay, so in fact you can write down a summary also. You can write down a summary also. So how that summary looks like. So ess, I'm sorry, what is the summary we can write? Summary table you can write. So what is the order of the system? 0 1 2. Okay, then kp, kv, ka. You can write down these values, so you can easily remember. So in this, what is kp? Here first case, type 0. So 1 by 1 plus kp, infinity and infinity. So this is 1 by 1 plus kp. So this is nothing but this is ess. So this is what? Step in. This is ramp. This is parabolic. Okay. Here you will have 1 by kv. Here you will have 1 by ka. Clear? So the here infinity and infinity, infinity and infinity, and the other case type 1 system 0 0, and here 0 0 0 0. Clear? So this is how you can easily remember for different cases. Okay. So what we saw was the steady state error for 3 cases. Okay, and also we have seen the for second order systems. Okay, so underdamped, overdamped, critically damped, also the peak overshoot, settling time, rise time definitions. Also we saw the natural and forced response, transients and steady state response. Okay, is this clear? Any quick doubts?
Yes, sir. I have a doubt.
uh, yeah, yeah.
Sir, like in the lecture, sir, while finding
Hmm.
the error, sir, take the feedback is one. If
No
feedback is
feedback.
not,
Which
yeah, yeah, please.
feedback?
Like while finding the error.
No, 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 no. See, feedback need not to be one. We can have anything also.
Yeah,
See,
like this is my question.
no, 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 no.
Like if
This,
the fit,
listen,
yeah,
listen, listen.
please.
Uh, this is your equation. Agree?
Yeah.
Okay. So this is your equation. Here, E of t is the error. Clear?
Yes.
Okay. If you find Laplace transform, that will be E of s. Clear?
Yes.
Yes, yes or no? So here in this image, what is E of s? This expression. Is this clear?
Yes, sir.
So now this is the image for y of s by r of s. Y of s by r of s, that will be like z by 1 plus g. Is this clear?
Yes.
So here this is unity feedback. but feedback not need to be unity. It can have another value also. In general, that is H. Okay. So G and H will have different terms. It means that, so what is the expression I have for KP? Limit S is tending to 0, that is G of S, correct?
Oh,
Yes or no? Let me show you.
yeah, for the
This one,
unity feedback.
this one.
Yeah, but it is for the unity feedback, right?
Unity feedback. If that feedback is not unity, you will get H of S also here.
Yeah, this is what I am asking.
That
Yeah,
is
thank you, sir.
correct. This is correct. Unity
Yeah,
feedback,
this
this is the definition. For general H, this is the definition.
yes, sir.
Okay.
This is what I am asking for you.
Yeah, correct, right.
Yeah, thank you, sir.
Okay. Any other queries? Okay. If there are no queries, we'll stop here and
Sir,
yeah. Yes.
yeah, like in the you can stop the recording if you want. I will
Ah, that's
general doubt.
fine. Yes, tell me.
Like like for the week one, I mail you about the two questions. It is not.
Oh,
Uh,
okay. I'll give the reply. Yeah. I will respond for that. Any other doubts?